There is a moment in every great science, a moment so quiet, so unremarkable, when the ground beneath everything we thought we knew begins very gently to crack. For decades, humanity operated under a beautiful illusion. We had built what physicists called the Standard Model of Cosmology, or Lambda CDM. And it was, by any measure, a masterpiece of the human mind. It described how the universe was born, how it aged, how it expanded, with a precision that was, frankly, terrifying. Not the terrifying of nightmares, the terrifying of staring into the abyss and having the abyss stare back with a spreadsheet. We knew the universe was 13.8 billion years old. We knew it was expanding. We had measured the rate of that expansion, a number called the Hubble Constant, and we were confident. We were so confident. And then we launched a golden hexagon into the dark. The James Webb Space Telescope, JWST, launched on Christmas Day 2021, and by 2022, it was sending back images that made hardened astrophysicists cry at their keyboards. It didn't just look deeper into space than any instrument before it, it looked deeper into time. Because in this universe, distance and time are the same thing. Light from a galaxy 10 billion light years away left that galaxy 10 billion years ago. JWST was reading a letter written before our sun existed. We expected it to confirm what we already knew, to fill in the details of our beautiful map. Instead, it acted like a demolition ball. Professor Adam Riess won the Nobel Prize in Physics for discovering that the universe's expansion is not slowing down. It is accelerating, tearing itself apart at an ever-increasing pace. For that discovery, he became one of the most decorated astronomers alive. And then, JWST gave him data. And he said something that sent a tremor through every physics department on Earth. We have misunderstood the universe. Not, our instruments were slightly off. Not, we need a small correction. We have misunderstood, capital M, the universe. This video is the story of how that happened, what it means, and why it might be the most exciting thing in the history of human science. To understand why this matters, you need to understand one number, the Hubble constant. Astronomers write it as h0. It measures the rate at which the universe is expanding, specifically, how fast galaxies are flying away from us based on their distance. The unit sounds absurd, kilometers per second per megaparsec. Let's decode that. A megaparsec is approximately 3.26 million light years. So the Hubble constant tells us, for every 3.26 million light years of space between us and a galaxy, that galaxy is racing away from us at x kilometers per second. The value of x is what the entire field of cosmology is currently arguing about, loudly. Method 1 comes from the European Space Agency's Planck satellite. Its approach is breathtaking in its audacity. 380,000 years after the Big Bang, when the universe was still a howling, superheated plasma, light was finally able to travel freely for the first time. The universe became transparent. And that first light? It's still here. We can detect it. We call it the cosmic microwave background, the CMB, and it is the oldest photograph in existence. Planck mapped this ancient light in extraordinary detail. Tiny temperature fluctuations of 1/100,000th of a degree. From those fluctuations, using well-established physics, scientists ran the equations forward across 13.8 billion years. Their answer? The Hubble constant is 67 kilometers per second per megaparsec. h0 equals 67. This is the early universe's prediction for what the present universe should look like. Method 2 belongs to Adam Riess and his team, called SH0ES, supernova H0 for the equation of state. Their approach is radically different. They don't model the past, they measure the present. Step by step, using what astronomers call the cosmic distance ladder. The first rung, Cepheid variable stars. These are stars that physically pulse, swelling and dimming in a precise rhythm. Crucially, the speed of their pulsing directly reveals their true brightness. Like a lighthouse whose flash rate tells you the wattage of its bulb. You see how bright it appears, you know how bright it actually is, so you calculate the distance. Perfectly. The second rung, Type 1a supernovae. Stellar explosions so catastrophically consistent in brightness that astronomers call them standard candles. You find one in a galaxy far beyond the reach of Cepheids, and its apparent dimness tells you exactly how far the galaxy is. Then you measure how fast that galaxy is fleeing. Speed divided by distance, the Hubble constant. Riess's answer? 73 kilometers per second per megaparsec. H0 equals 73. 67. 73. That's only an 8% difference. Does that matter? You have no idea. An 8% difference in the Hubble constant doesn't just tweak a number in a textbook. It changes the age of the universe. It changes when the first stars formed. It changes the entire timeline of dark energy, the mysterious force pulling the cosmos apart. It changes whether the universe will expand forever or eventually, somehow, reverse. And, crucially, both measurements are extraordinarily precise. Both have error bars so small they don't overlap. This is called the Hubble Tension, and it has been growing for years. But then JWST arrived, and scientists thought, finally, we'll fix this. They were wrong. When the Hubble tension first emerged, the scientific community had a perfectly sensible explanation, thank you very much. They called it stellar crowding. Here's the problem. Cepheid stars don't float politely alone in empty space. They live inside galaxies, dusty, chaotic, star-packed galaxies. And when Hubble photographed them, the images were fuzzy enough that nearby stars blurred together. If you're accidentally measuring 2 stars while thinking you're measuring 1, you miscalculate the brightness, you miscalculate the distance, you get the wrong Hubble constant. Simple. This was not a conspiracy. It was a genuine, well-reasoned scientific hypothesis. Adam Riess's measurements, the argument went, were being corrupted by his instrument's limitations. When JWST arrived, with its infrared eyes that cut through dust like a laser through fog, with resolution that makes Hubble look like a disposable camera, it would separate the blended stars and bring the number back down to 67. The physics community waited. Some of them, frankly, were gleeful. "Riess is wrong," they whispered. "JWST will prove it." They were wrong. JWST did not fix the Hubble tension. It confirmed it. It cemented it. In a cascade of papers between late 2023 and 2025, Riess and his collaborators published JWST cross-checks of their Cepheid measurements. They compared Cepheids against red giant stars, a completely independent calibration technique called TRGB, the tip of the red giant branch. They cross-checked with JAGB stars, another independent rung on the distance ladder. They triple-checked every assumption. The number stubbornly, infuriatingly, beautifully held. 73 kilometers per second per megaparsec. JWST didn't eliminate the stellar crowding. It showed the crowding correction was already accurate. The 8% gap is real. The models are wrong. Something we don't understand is happening to space itself. But wait, there is a third voice in this argument, and she complicates everything. Professor Wendy Friedman of the University of Chicago leads an independent research group using You guessed it, a completely independent method. Her team relies more heavily on the tip of the red giant branch technique, finding the precise moment when red giant stars undergo a nuclear explosion, a brightness flash so standardized it's like a cosmic flare gun. Her answer? Approximately 70 kilometers per second per megaparsec, right between the two camps. And that number, my friends, is either a clue or a catastrophe, depending on who you ask. Is Friedman finding the true value, and both Riess and the Planck team are slightly wrong in opposite directions? Is her intermediate value evidence that the distance ladder itself, the entire chain of calibrations stretching from our solar system to the edge of the visible universe, has a subtle, systematic crack in it? Or, and this is where it gets terrifying, is the universe simply not obeying the rules we wrote for it? Is there new physics hiding inside that 8% gap? Let's go deeper. The Hubble tension is the most precise and statistically significant crack in our cosmological model. But it is not the only one. When JWST turned its golden eye to the deepest, most ancient reaches of space, to the universe as it was just 300 to 500 million years after the Big Bang, it found galaxies that had absolutely no right to be there. They were too massive, too mature, too well-formed. Like opening an ancient tomb and finding a smartphone. The internet called them little red dots, compact, red-shifted objects that initial spectroscopic analysis suggested were galaxies containing as many stars as our own Milky Way, but formed in a fraction of the time it should have taken. The standard model of galaxy formation, the one baked into our Lambda CDM framework, says galaxies build themselves slowly, bottom up, small clumps merging into larger ones over billions of years. But JWST seemed to be finding massive, mature structures that formed in cosmic microseconds. Panic rippled through the field. And then, in 2024, a team led by Catherine Turowski published an analysis that put some of those fears to rest. Many of the little red dots she and her collaborators found were being misread. At their hearts lurked supermassive black holes in an active feeding phase, so bright, so luminous, that they were artificially inflating the inferred stellar mass. Remove the black hole's contribution, and many of these galaxies shrink to a more comfortable size. Science corrected itself. Good. That's what science does. But here's the thing no one is quite saying loudly enough. Even accounting for the black holes, even removing those anomalies from the dataset, JWST is still finding roughly twice as many large, mature, well-structured galaxies in the early universe as the standard model predicts. The crisis was exaggerated, but it wasn't invented. Half the anomaly evaporated. Half remains, unexplained. JWST found something else that has cosmologists quietly losing their minds. A galaxy nicknamed the Big Wheel, a fully formed, massive spiral galaxy observed when the universe was less than 1 billion years old. Spiral galaxies, by our models, need billions of years of gravitational choreography to develop their elegant arms. The Big Wheel apparently skipped that cue. And then there are the shapes. In a landmark 2023 study, astrophysicist Viraj Pandya and colleagues cataloged hundreds of early galaxies in JWST data and found something nobody expected. They weren't spheres. They weren't disks. They were elongated, stretched, like cosmic cigars. In the standard model, early galaxies should be roughly spherical. Dark matter halos collapsing symmetrically under gravity, pulling gas inward equally in all directions. But what JWST found looked more like filaments, spindles, needle shapes. Why does this matter? Because the shape of early galaxies is a fingerprint of dark matter. And if the shapes are wrong, if cigars dominate where spheres should, then the nature of dark matter itself might be different from what we assumed. The leading hypothesis goes like this. We have always assumed dark matter is cold, meaning it consists of slow-moving, heavy particles that clump easily under gravity. But what if it isn't? What if dark matter behaves more like a quantum wave, what physicists call fuzzy or ultralight dark matter? Or what if it's warm, lighter, faster-moving particles that can't clump on small scales the way cold dark matter can? Warm or fuzzy dark matter would produce elongated structures. It would resist forming the dense spherical halos our models predict. It would produce, exactly, cosmic cigars. The scaffolding of the cosmos might be made of something fundamentally different than we thought. The Hubble tension is the loudest alarm, but it is not the only one. Meet S8, the sigma-8 tension. The Standard Model doesn't just predict the expansion rate of the universe. It also predicts how lumpy the universe should be, how clustered matter is, how pronounced the great walls and voids of the cosmic web are. This clumpiness is quantified by a parameter called S8. The Planck satellite's model of the early universe predicts a specific level of clumpiness in the present universe. Surveys of weak gravitational lensing, the subtle bending of light from distant galaxies by dark matter in the foreground, measure the actual clumpiness of the present universe. The universe is smoother than it should be, less clumped, more uniform. The dark matter filaments are there, but they are softer, more diffuse than lambda CDM predicts. Two independent cracks. The Hubble tension. The universe is expanding faster than predicted. The S8 tension. The universe is smoother than predicted. Both point in the same direction. Something has been wrong with our model since the very beginning. So what fixes it? What could resolve both tensions simultaneously? One of the most compelling current proposals is called early dark energy, EDE. We know that dark energy exists today. It's the force accelerating the universe's expansion right now. The Standard Model treats it as a constant, a background energy woven into the fabric of space-time, never changing. Einstein called it the cosmological constant. But what if dark energy isn't constant? What if there was a brief, violent pulse of additional dark energy in the very early universe? Perhaps in the last moments before the CMB released, that temporarily kicked the expansion rate up. A kind of cosmic booster shot that fired once and then dissipated? This early dark energy pulse would have two effects. First, it would have caused the universe to expand faster than the Planck model predicts, which is exactly what Riess observes. If the early universe expanded slightly faster, space formed in a slightly different way, and the Hubble constant we measure today is higher than the CMB predicts. Second, an extra injection of energy in the early universe would have smoothed out the formation of large-scale structure, reducing the clumpiness, which is exactly what the S8 tension describes. One mechanism, two solved problems. It is an extremely elegant idea, which means, in physics, it is probably wrong in at least one important way. But it might not be entirely wrong. Other proposals abound. Interacting dark energy that slowly decays into dark matter. A new particle, the sterile neutrino, that mediated interactions in the early universe. Modified gravity theories that subtly alter how matter clusters on cosmic scales. None is proven. All are being tested with James Webb. It is tempting, very human, very understandable, to hear all of this and think, science got it wrong. The experts were mistaken. Maybe we can't trust any of it. I want to push back on that interpretation as hard as I possibly can. Every major revolution in the history of science began with exactly this: a precise, well-verified measurement that didn't match the model. Not a vague feeling, not a philosophical objection, a number that didn't fit. Newton's gravity was overturned by the precession of Mercury's orbit. One planet, one anomalous path. one persistent number that refused to fit the equations. Einstein's general relativity was born. The CMB itself, the discovery that validated the Big Bang theory, was an anomaly first. Radio astronomers Penzias and Wilson kept detecting a persistent, infuriating background hiss they couldn't explain. That hiss turned out to be the afterglow of creation. The Hubble tension is not a failure. The S8 tension is not a crisis. They are invitations. They are the universe leaving us a trail of breadcrumbs into territories our imagination hasn't reached yet. Let me tell you what I think about all of this. You, the person watching this video, are, in the deepest physical sense, a rearrangement of atoms that were forged inside a star that no longer exists. The iron in your blood was made in a stellar core and scattered across the galaxy by a supernova explosion, billions of years before our sun ignited. You are not a passenger in the universe. You are made of it. The universe is 93 billion light-years across, and growing. It has been expanding for 13.8 billion years. In the entire sweep of that history, human civilization, the part of it that does science, that builds telescopes, that writes down equations, occupies roughly a 10,000th of 1% of cosmic time. We are a fraction of a second's anomaly, a brief, improbable flicker of consciousness on a speck of rock, orbiting an ordinary star in the outer arm of a middle-aged galaxy among hundreds of billions of other galaxies. And we decided to look up. We decided that the darkness wasn't a limit, it was an invitation. We built mirrors. We put them in space. We aimed them at the oldest light in the universe, and when that light told us something we didn't expect, we didn't look away. We refined the measurement. We built better mirrors. We sent them further. The fact that our cosmic map is breaking isn't a failure of human intelligence. It's the highest expression of it. Because only minds that are genuinely committed to the truth, only minds willing to be wrong, to have their certainties demolished, to start over, can produce knowledge that lasts. We don't know what lies beyond lambda CDM. We don't know yet whether the Hubble tension points to new physics or a correctable error. We don't know whether dark matter is cold, warm, or a wave. We don't know what early dark energy is made of, or where it went, or if it was real at all. But we are asking the questions. With gold hexagons in the dark, with equations on whiteboards, with young PhD students staying up at 3 in the morning, staring at data that doesn't make sense, feeling that first trembling sensation of being at the edge of something enormous. The universe is broken. Long live the new universe. If this video made you feel something, wonder, vertigo, excitement, or even just that pleasant feeling of your brain expanding 3 sizes, then I hope you'll subscribe and stick around. Because the cosmos is not done surprising us, and neither are we. I'll see you out there, in the dark, looking up.